Hello YouTube, I have acquired some water. Hopefully this makes it so my voice is a little less raspy and I cough less. Who knows? Today, we're going to be talking about how to take the stuff we learned about last time with orthogonality and 2D motion and translate that into projectiles. Interestingly enough, just like with normal projectiles, these problems actually tend to be a little bit easier because you sort of have some specific things that will be true for them. But that also means that you can seemingly have less information available because there's so much stuff you're just supposed to already know about the object. So let's dive in. In particular, modeling motion in a projectile, especially if it's in 2D. Big one for that is going to be generating systems of equations using a 2D projectile stuff. And this is unit 1.9, 2D projectiles. Great. So, gravity goes down, not sideways. And this has some kind of counterintuitive effects. Well, for a lot of people, it's intuitive that if you have something that's moving sideways while it's traveling, so if you like throw something to the side versus if you just drop it, that those two things will behave inherently differently. After all, if you're looking at the path of each object, your first object would travel like this, your second object, which you're showing sideways, would travel like this, where it's parabolic. What's kind of counterintuitive about that is that even though their distances are completely different, the y direction is going to function the exact same way in both cases because x and y are orthogonal. Moving sideways doesn't bring you any closer to the ground, but it also doesn't bring you any further. So if you're looking at the y direction, velocities of these things at any given height, let's say, actually it would be 0 at the beginning, so I should not do that. Let's say at this height you're looking at the y velocity, it's going to look something like this. Well, if we come over to this one, the y velocity will be the exact same. And the y velocity will actually be getting exponentially bigger as you go because it's accelerating, right? We've got that gravity going down. But it'll be the same in both cases. And if we're looking at the x direction velocity, well, here the x direction velocity is 0, the x direction velocity here is 0, the x direction velocity here is 0. Here we'll have some initial x velocity. We'll have the same initial x velocity, and we'll have the same initial x velocity here. And the reason that this point is closer to this point in the x direction, this one is closer to this one than this one is to this one, is simply just because we're going down faster. So it takes us less time to drop that distance because we're going faster in that direction. So again, some kind of weird, some kind of weird or unexpected consequences there that can be a bit counterintuitive. Specific thing that can help with problem solving. At the top, your velocity is not going to be 0 if it's a two-dimensional projectile. It's actually going to be, and I use the top to mean the maximum height if you like have a projectile that you launch and you just let it do its thing. It should be the same as Vx naught. This is specifically without air resistance. And the reason it'll be the same as Vx naught is because the velocity in the x direction is constant, so it's never changing. This is actually also going to be the minimum velocity of the object. So a lot of times problems will literally just be like, the minimum velocity of the object was 20, the initial velocity was 40 meters per second, what's the launch angle? And you're like, what, pardon? But using that idea there, the minimum velocity is the same thing as just Vx naught, which is the same thing as just Vx because it's not changing, it's just Vx. And so you could use those two things together to set up your components for your original vector and figure out what angle things are at. Or anything else, right? There's a lot of ways that can get used in problems, and that was just sort of one specific one. All right, so let's do a sort of broad general example of this, talk about some repercussions of that, and then do a more specific one. So this is the range equation. It's an equation that sort of tells you how far something will go, depending on its launch angle and depending on its initial velocity. A second thing that I probably should have put in the example, I want to try to maximize it, like figure out what the maximum range that something will go is. Doing that, I think we can actually skip the stop copying problems one and go straight to this. So we've got a projectile, and the things that we know are the launch angle, which I'll call theta, and the launch velocity, which I'll just call v naught. So these are our givens. What we want to find is if our projectile, which goes in an arc like this, very explicitly, because Vy keeps decreasing over time, it will never reach as high as it would go by the time it got here if there wasn't gravity, because gravity is pulling it down. So very, very specifically, please be careful of this. This arrow should not point at the top. This arrow should point above the top. What we're looking for here is the delta x that this thing goes when by the time it gets back to level ground in terms of v naught and theta. Now you're always allowed to use g, it's just a constant. So g is fine too, and that one will equal ay. There are a lot of ways you could approach this problem. I think my personal favorite, just because I like throwing zeros into numbers, would probably be to say that like the time to the top is half of the total time, and we could figure out the time from the top to the bottom very easily because we know that the initial velocity for that case would be 0. Not going to do that now because that does tend to be kind of a more complicated way to think of it, even though the math kind of winds up being easier. And let's just sort of list out our givens, do our same setup, do our approach, figure out what we can. So in the x direction, our equation is going to be delta x equals vx times time, because it's a constant velocity in that direction. In our y direction, we've got kinematics, because it's accelerating. So in our x direction, delta x is the thing we want. We don't know it. Vx we don't know directly, but if I pause for a second, v naught is going to have two components. Vx, which will be equal to v naught times the cosine of theta, and vy. Specifically vy naught, which is going to be equal to v naught times the sine of theta. All of a sudden, we've taken these variables that we don't have and we've represented them in terms of givens. So not really a variable anymore. This is now effectively just a given. And we don't know the time. But if we look in our y direction, we know that ay is equal to 0. You know that vy naught is equal to v naught times the sine of theta. If we think about the symmetry of the problem, when it's landing, our final velocity is actually going to have the same components as our initial velocity, but down instead of up. This is coming from sort of the 1D projectile thing. If you want to rederive it or reprove it, the big thing is that the time on the way up needs to be the same as the time on the way down, or that delta y is equal to 0. If you use it, delta y is equal to 0 with vy naught squared equals vy squared plus ay times delta y, 2ay times delta y. We haven't really done this proof yet, so it does make sense to do it briefly. This is 0. So what that tells us is that our two velocities in the y direction are the same as each other when we square them. If that's the case, that should mean that they're without the squared. That would mean that the object is going up when it lands, which doesn't make sense. Or it's going down when we launch it, which means it wouldn't ever go up at all. But because of this squared, when we square root both sides, we actually introduce a plus or minus. The only way this conceptually makes sense is if we've got plus or minus Vy is equal to minus or plus Vy naught. So whichever one is positive, the other will be negative. Whichever one is negative, the other one will be positive. And this tells us that we can say over here that our final y velocity is actually just going to be equal to negative v naught sine theta. Our acceleration in the y direction is going to be negative g because we're just going to have gravity going down. This is super, I don't know why I said ay is 0, delta y is 0. This is going to be super useful because if we want to find the time, we've actually got 4 out of the 5 pieces of the kinematics equation now. Well, this equation with these 4 is really easy for time. We can take that and bring it over here, plug it in, and that'll get us delta x. So doing that out, we've got Vy is equal to Vy naught plus ay times t. Plugging in our givens, we've got phi naught sine theta, negative, is equal to positive Vy which is V naught sine theta plus negative g times t. We're solving for t, so we need to get rid of V naught sine theta. That'll give us negative 2 V naught sine theta is equal to negative gt. Divide each side by negative g, divide each side by negative g. And we're left with 2 V naught sine theta divided by g is equal to our time. This isn't our answer, but it's pretty useful because we now have our time in terms of our givens, V naught, theta, and g. If we bring that over to this equation for constant velocity, so this is sort of our step 1, and this is our step 2, we know that delta x, the thing we're looking for, is going to be equal to Vx times our time. Well, Vx, if we plug in, is V naught times the cosine of theta. Our time is V naught times the sine of theta, which is all times 2, divided by g. For me, this is ringing some alarm bells on some trig identities. If I quickly look up trig identities, we can find sine of a double angle, I believe, which I don't super remember off the top of my head, but 2 times sine theta cosine theta is equal to sine 2 theta. Great! So I can replace one of my trig identities. Do you have to do this? No. But this does make it prettier. It also makes it so that when we're doing this here, we've got V naught times V naught, which is V naught squared. It's easier to find our maximum. So this is our answer for our range equation. Anytime you're trying to find how far a projectile on level ground goes, this will do it. You do need to know the initial velocity, you do need to know the launch angle, but if you have those two things, this is just it. I'd recommend hanging on to this one. It can save a lot of time in problems because that process we just went through took like 10-ish minutes. But you have it now. If we want to maximize this, the question is, how do we make this as big as possible? And the big thing that specifically by changing angle. We could make it as big as possible by having less gravity. So if you launch something on the moon, it'll go further. We could make this as big as possible by launching it faster. That actually increases the distance squared. So every little bit we do to launch it faster makes it go way further. The other way we could maximize this is by having our angle change the sine of 2 theta to be as big as possible. If we want to maximize this, we want the sine of 2 theta to be max. Well, that happens if you do calculus and take the derivative with respect to theta. It'll be when that equals 0, which is when cosine theta equals 0. You also could just know that the biggest a sine function can go is 1. I'm going to use that way. Well, this is equal to 1 if we take the inverse sine of both sides. Sine of the inverse sine of 1 is either 90 degrees if you're using degrees or pi over 2 if you're using radians. If we then divide each side by 2, that'll give us that our angle that maximizes this thing is equal to pi over 4, which is 45 degrees if you prefer that. What I think is particularly interesting about this is that there's actually a really nice conceptual approach here. When our angle makes it so that we've got exactly the same amount of Vx as we do Vy, because we're exactly in the middle angle, we go as far as possible. And conceptually, a way to think about why this happens is, let's break down the two things that give us more range. We can either have more Vx or we can have more time. More Vx means that for each second we spend in the air, we'll travel further to the side. So the further down you bring the launch angle, the more Vx you get, meaning the faster you'll be going for each second you're in the air. But, which is why if you launch it straight up, it won't go anywhere, right? You don't have any Vx, so you just don't, you just go straight up and then land back down in the same spot. If you launch it straight to the side, you don't go anywhere for the opposite reason. You have no time in the air. You've gone as fast as you can sideways, but literally as you launch it, you're just launching it straight into the dirt. So you need Vy in order to get time so that while you're going really fast, you actually go somewhere. When you perfectly balance those two things, you go as far as possible. A follow-up question for this that can come up sometimes that's sort of like a did you really get it though, is thinking about hills and cliffs. So again, we're trying to, if you've done maximizing areas of shapes, with a given perimeter, if you have an shape with a fixed perimeter and you're trying to maximize the volume for a rectangle, for example, that happens when you make it a square. This is actually kind of useful for thinking about how, weirdly enough, to size a fish tank. If you have this really long skinny thing, adding a little bit more to the length of it doesn't really give you a lot more area or a lot more volume, because looking at a shaded thing, if I had added a little bit more in blue over here, this isn't particularly large because we're only increasing, this line is the line that's getting added every time we add a little more to the right. But if I add a little more on the bottom, look at how much longer the line I have to draw is to add more on the bottom. So the area you get by adding just a little bit on the bottom or the top is huge compared to the area you get on the side. Anytime you have them out of whack with each other or out of balance, adding in the opposite direction will be more efficient to bring more area or maximize what happens when you multiply the two things. There's just different ways to conceptualize it. If that doesn't make sense to you, that is no problem at all. Specifically on the physics side of things, let's say you're launching something off a cliff. Well, this would be the normal range equation. But then you start falling. Now, while you're falling, you get to travel sideways kind of for free. So what winds up happening is if you launch it higher than that, you'll get something like this. If you launch it lower than that, you'll actually get something like this, which goes a little further, until eventually when you launch it low enough, it'll just come back down again. And the reason that this is happening is because instead of having a Vx and a time that are perfectly balanced and the same size as each other, what a cliff does is it makes your time artificially bigger. So if you want these two things to be the same size as each other, but you've got this really big time, the only way you can do that is by bringing up your Vx as well to help balance it out, which means you want to launch it further down so you get more Vx. Now, you do lose some time to do that, but you're basically taking these two things where this hand is your time and this hand is your Vx, and you're like, what did the cliff do? Well, the cliff brought the time up here. I want them to be on the same level as each other. So I bring one down and the other up until they meet in the middle. And overall, you'll be able to go much faster if you launch off a cliff. The flip of this, or the inverse of this, is if you're launching up a hill. If you're launching up a hill, it'll look something like this, where this is your hill. And then when you do your launch, if you launch it basically straight up, versus if you launch it more to the side, you can kind of see it just like smack straight into the hill. When you have the hill, what the hill is doing is it's actually taking your Vx and your time, and it's saying, well, you're going to hit a hill. So you don't have anywhere near as much launch time as you used to, and it's actually kind of approaching it from the other angle. Your Vx stays the same size that it used to, but your time is like tiny comparatively. So to fix that, you have to take your Vx and bring it down. You're again taking this thing where they start out as balanced, but this time, instead of having your time get really big artificially, you're having your time get really small. So to balance it out, you need to launch more up to bring your time up, which does bring your Vx down, but until they become even with each other, that'll happen. So maximum launch distance on level ground is when they're the same size as each other. Maximum launch distance on a cliff is when you're aiming down more than you normally would, so below 45 degrees, above 0 but below 45. When you're aiming at a hill, maximum launch will be above 45 but below 90. Because if you launch above 90 degrees, it goes backwards. Yeah. I feel like there's one more example problem here. It's getting kind of late, and this video is getting pretty long. Whoops. Let's see how long this one's going to be. Oh. If there was going to be another example problem, I forgot to write it and just have the one from the last video. So, I'm calling it. Goodbye, YouTube. Hope you have a great rest of your day. Let me know if you want to do another example of a 2D projectile, like one with numbers or something that totally makes sense. But otherwise, enjoy and good luck on the practice problems.